All right. Yeah, after that, I'm just gonna join voice one. People can ask some questions, maybe something like, can you do some more explanation about how to work with recursive types or how to do overloading? And we have 3 hours. I'm not sure if I can fill the entire 3, and I'm not sure if you guys can hold out for the entire 3, so we'll just see how that turns out. But I'm gonna do sessions of 45 minutes and then a 15-minute break in between, so we can get something to drink, get something to eat. Let's see if it's fixed. Yeah, it looks good. Okay. All right. Yeah, I got access to the server now, so I'm gonna join the voice channel. It's up to you if you want to mute the stream, because you probably have double audio right now, or mute me on the Discord server. Let's see, how do I want to start? Right, yeah, so if you have questions, feel free to ask. You can either send a message in Twitch chat or in the text channel, the questions channel, or you can let me know that you want to ask something in the voice chat, and I'll listen to you. The first thing I want to do, of course, is give you guys the Google Drive link. So that would be... There you go. So there's nothing in there right now, but I'll see if I can drop some stuff in it. Yeah, I'll do that later down the line. So I'll start with the presentation then. Although I must say I was a bit hastily preparing yesterday. I don't want to do that. I want to do... Strange. Let's do it like this. All right, so I've actually, this is now the third year I'm giving the workshop, so I have some content from previous years. And let's see, yeah. So every year I try to predict what's going to be on the exam, and every year I think I'm right, and every year it turns out that I'm actually wrong. So instead of trying to tell you guys, yes, this is definitely going to be on the exam, I'll give you what I expect to be the case. And of course, also with the course being so different this year, it's going to be even less certain if it's actually going to be covered on the exam. But you can be pretty sure that there's going to be at least something of every week. And of course, if that includes week 1, it'll be pretty simple content, but it slowly works its way up to overloading with implicits. So what I expect to at least be on the exam is going to be type inference. That's something that you've done, I believe, in week 2, where you have the F1 and you get some example inputs, some example outputs, and then you have to determine what the types of the inputs and outputs are. It's going to be something with a list, so you have to know how to do recursion with those. And I'm also going to cover some useful functions that you can use on lists. It might be helpful. Recursive types is pretty much definitely going to be on the exam. That's something like, where you have a type defined person, and then the person has some parents, and the parents are either unknown or a known person, something like that. Then higher order functions is definitely going to be in there. And I'd imagine that currying might be in there as well. It's not necessarily part of higher order functions, but it is pretty often related to each other. Folds is probably also going to be part of higher order functions. Though if it's on there, it'll likely only be one exercise. And then, of course, we have program reasoning, which is a subject that you can very easily score some points on. You don't need any programming knowledge or know-how to do evaluation because you're just applying rules, and the same with induction. If you just hold yourself to the template of induction and you perform the right steps, you can easily score some points on this. And overloading is, well, pretty much guaranteed going to be on there as well, and likely that will be with implicits, though, as you've probably seen in the end of the exercise with overloading. There's a different way you can do it with overriding case classes or case objects. So I kind of cut down on the contents of the presentation itself, just because I tried to rewrite it from clean into Scala, and then I kind of realized that the issues that were present in clean, at least from your submissions, seem to not really be the case anymore in Scala, probably because of the familiar syntax. So I heavily cut down on it. I kept these, and it'll be a pretty short presentation, and then we'll see what to do. So first thing is, because there's going to be a lot of lists in this presentation, and this syntax here takes up quite a lot of space, so I'm going to make this shorthand for this, which, especially if you worked with Python before, it should be pretty familiar. So for comprehensions, it basically allows you to do either a zip or a Cartesian product on top of also a map and a filter at the same time, which can be very useful because that can abstract a lot of the difficulty away from whatever you're working with. So in this scenario, can I hear myself? That's weird. Whatever. Yeah, so for the zip, what that essentially does is it combines the elements of the list in such a way that you only get the ones with the same index. And really, if you look at the part where you say, well, this is the pattern of the elements that I'm going to take out of my list, out of this zipped list, and you look at the yield, it's exactly the same thing. So really, this list comprehension doesn't do anything else than just this zip right here. But if you use a semicolon, then it'll say I'm going to have every possible combination of these two elements, and then I'm going to yield this tuple of x and y. And of course, you can also specify some extra condition in which, only do this yield if this holds. So this is your filter part. And then over here, this is your map part. We don't do anything really special for this map. In this case, you turn it into a tuple, so it is different. In this case, not so much. So if we have an xs of 1 and 2 and a ys of a and b, then the results of these expressions will be a list of tuples of 1 and a and 2 and b, because these have the same index, which is a requirement for zip. And for the Cartesian product, it's every possible combination. So naturally, that's 2 times 2 is 4 elements. And then you have this list. And for the extra condition, you can basically say, well, if it's divisible by 2, only then do I want these elements. So 1 isn't divisible by 2, so we only take the ones that include a 2. Now, you're going to get a list of available functions on the exam. It's going to be an appendix. I'm not entirely sure what sort of format they'll use for it. They'll definitely put the types there. They might give you a small textual explanation of what the function does, maybe an example, but it's still useful to know what they do beforehand, and especially useful to be able to read what they do from the type definition alone. So, assuming that you have these two lists, XS is a list of general type A and XSS is a list of lists of general type A, then you can call, for example, flatten on XSS, which will turn a list of something into just a list of something. I got a question from Christy. Let's see. Is the if f modulo 2 equals 0 with 1 or with 2? Oh, did I write that wrong? Yes, I did. Yeah, it's with 2. That should be with 2. Good call. Yeah, so with the flatten, basically you just, if you've worked with the plus plus operator before in lists, you basically just apply that to all sublists of this list. So you just glue them all together, and this can be quite helpful if you're ever in a situation where you think, well, I need a list of integers, but all I have is a list of lists of integers. Chances are you're going to have to do flatten at some point. Maybe you want to do something first with that list of integers and then flatten, or maybe you want to immediately flatten. But if you realize that whatever type your expression is, it doesn't line up, and you need it to be one order of magnitude lower, flatten is a pretty safe bet. Then, of course, we have index of, which you might have used already. It takes some argument of the type containing that list, and then it tells you what the index is of that element as an integer. Some of the things that you might not have seen before are last and init. They're essentially the same as head and tail, but they go from the right side. So the last is basically the head from the complete endpoint of the list, the last element, and init is as opposed to the tail where you say it's everything aside from the head. The init is everything aside from the last, which you can also see here for some example calls. Then we have the functions take and drop, which takes some integer and they will either take that many elements from the list or drop that many elements from the list. And we also have a take while, which probably looks familiar. You give it some function, it outputs a boolean, and it'll take, just like take, elements from your list until this function is false, and then it stops. And the same thing with drop, but then it drops instead. Of course, we then have the filter, which takes a function from some value of the type of that list, and it returns a boolean, and it'll only include the elements for which that boolean returns true. So I forgot to rewrite this part, but just imagine that it says this list dot and then this thing here. I did it right here. Okay. So continuing, I have quite a few of these. There's of course the map, and I think this is a really good example of how to read program behavior from just the type definition. Because if you look at XS, then XS is some list of general type A, and when you call map, then you have to pass it a function that takes a single A and turns it into a single B, B being a general type. And then naturally, if you have a list of A's and a way to turn a single A into a single B, then of course you can compose a list of B's. So being able to read behavior from a type definition can also be very useful when you get that list of available functions. Then here's an example, basically says, well, I have this list of integers, I'm going to do a map, and then for each element I'm going to return -2. So then 1 minus 2 equals -1 and so forth. Reverse should be pretty straightforward. Sorted, this actually isn't complete because it requires that whatever this type A is can be ordered. So there's that has something to do with overloading. Important to keep in mind that if you order or if you sort something, it'll always be ascended or ascendingly, so from small to large. And if you, for example, sort a list of tuples, it will first be sorted on the first element of that tuple. Then if you find two tuples for which the first element is the same, then it'll sort it on the second, then on the third, and so forth. So if it says, you have a list of resulting tuples, sort it based on the first element, you can just say .sorted, and it's done. Then you have two alternatives to sorted called sort by and sort with. And with sort by, you basically say, well, before I check the ordering of my elements, I'm going to first apply this function and only then order them. So what I do in this case, for example, is I say for every element, I'm going to negate whatever that is. So I'm going to do minus that element, and then I'm going to sort them. So it'll basically sort these elements based on the list -1, -6, -4, -2, and then coincidentally you end up with the list sorted descendingly. And the same thing in this case can actually be achieved with sort with, which takes a function that takes two values of that type in the list, and it returns a Boolean, basically saying you can kind of see it as a chain of all of these things holding, because by default it'll be with let's see if I get this right. Yeah, mirrored on the video. So it'll be with less than. So if you can kind of envision that list with the elements in there all separated by less than, then that should all hold, of course, ignoring the fact that two elements can be the same after each other. So in this case, you can say, well, I want to sort with larger than instead, because the default is smaller than, and then you also get the list sorted descendingly. Then for all and exists, you've worked with before, you've made it yourself before, and it just takes some predicate, which, let's see. So I get a question, will the elements in the list also change when applying the F? That's for sort by, I assume. They will not. The resulting list will have the same elements as the original list, but it'll be sorted according to something else. So for example, say you have a list of tuples and you want to sort them based on the second element, then you could call something like, gonna take this here, you could call something like xs.map, and then take some parameter from your, or take some element from your list, and then sort it on the second element of that list. Obviously this gives a syntax error because this is not right, but the syntax in this case, the intuition is correct. And in that case, it would sort it based on the second element, but it would still return those tuples. Yeah. Let's see, I got another question. If there are equal values, should you use larger than or equals to? That's a good question, because yes, in fact, if it's a chain of larger than, if they're equal to each other, it's going to be incorrect. But with some clever Boolean manipulation, you can actually define. Yeah, let's see. So if you know what to do when like if you know when x is smaller than y, you actually also know when x is larger than y, because that's the same as saying y is smaller than x. And in fact, you can get x is smaller than or equal to y by saying not x is larger than y. And then that works for the same, but with smaller than. And in fact, you can also define equality with this by saying x is not smaller than y, nor is x larger than y. So if you know this one, then you can figure out all of these, and it'll implicitly, maybe a bad choice of words, but it'll automatically, I suppose, use this one instead. But good question. All right, So then, yeah, for all n exists, it takes some predicate which takes some element from your list and returns a Boolean, and it'll only return true if for every element this function returned true. The exists is quite similar, but it'll return true if it happened for at least one. If it happened for none of them, if for none of the elements this function returned true, then only then it'll return false. XS.contains, this one's quite useful because it abstracts a lot away from having to write this yourself. So you can just give it some element or some value of the type that it contains, and then it'll tell you if it's in there or not. And of course, distinct, something that you've used before in the FQL exercise, it should look pretty familiar too. And then for tuples, I had this giant list previously, but really in Scala, there's really just this. If you want to get some, so if you have a tuple with 3 elements, some A, some B, some C, all general types, and you want to get the first element, then you just call ._1, and it'll give you something of type A. In this case, they're all integers. They don't have to be. What's important to note here is that for some reason it doesn't start counting at 0, which is a bit strange because that's what you're used to, but just keep that in mind. So for the first element, you just call ._1. Then for fold left and fold right, I'm going to cover fold left for now because I think it's more easily understandable in terms of the syntax. So intuitively, something that you might have seen before is something like this. So if you have a list of, say, 3, and then let's do it like this. So if you then do a fold left with, for example, this, then intuitively what you can do, and you have some starting value, of course, so that will be, this is the right order? Probably not. Maybe something like this. So if you have some starting value here and some reducing function here, then and that reducing function is infix, so it's between its 2 parameters, then you can intuitively take the starting value, replace the empty list or nil by it, and then replace all of the cons operators with the plus, and then you get your result. That makes it very simple to understand, but only for infix operators, because you might have something where, for example, you take the maximum of something and then that isn't infixed, and you have to figure out what sort of lambda expression you want to give to your reducing function. So let's see. So basically what happens is this is a fake implementation of fold left, because normally you call it, the list dot fold left, but here it's just a function that takes 3 arguments. So here it immediately takes some list of A's. It takes some accumulator of type B. This is where you're going to store your intermediate results. And then you have some reducing function here, which takes a single B, a single A, and it returns a new B, and then the output of the whole function is another B. And if you just look at the types, it makes sense that this reducing function returns a new B, because say that instead it will return a new A, then you have an entire collection of A's over here, and you have a single B, and then you apply this once, and then you've used your B, you've used one of your many A's, and then you get a new A, but then what do you fill in for the B next time? So obviously this should return a B, so you can keep applying this function as long as you can take an A out of your list of A's, because this generation of a B can occur for as long as you can take an A, because this B here is just going to put back into this B over here at the following iteration. We'll see how that is done exactly over here. So what you do is you match on your list, and let's go to this one first, the most general case, sort of, where you say, well, if I can split this list into a head and a tail, then I'm going to immediately call fold left again. I'm going to give it now the tail of my original list, because this excess over here shadows this one over here. So this excess will be the tail of that one over here. And then the second argument that it gets is the accumulator. But instead of just giving it this accumulator, you actually apply this reducing function to the accumulator and whatever element you've taken out of your list here, resulting in a new accumulator, again of type B. And then you just give your reducing function again, because you need to keep track of it somehow. Now, if you cannot take an element out of your list, then naturally, as I said, you cannot produce a new B, because you need an A to return a new B. So really the only option that you have of giving a B is just returning that accumulator. And in fact, it might start to make a bit more sense to you, but if you're having trouble understanding the intuition, a fold is really just, especially a fold left, is really just a canned for loop, because something that you've probably done a lot is something like a variable of type integer. That's not the right syntax. Variable sum of type integer equals 0, and then you have, you know, some list val xs equals, you know, again, you're not allowed to use variables, but just as an example for how you do it in imperative programming, you get a list of 1, 2, 3. You have a sum of this, and then you say for every x in my xs. I'm not sure if this is correct syntax, probably not. Imagine it is. Imagine it's Java syntax, where you say, you know, I have an integer x, I get it from my xs, and then for every single one, I do sum equals sum plus x, and then at the very end, you just say return sum. This is something you've probably done a lot before in imperative programming, and really all of the components are here to turn it into a fold, because, you know, this is the list that you're looping over here. This is whatever value you're starting with, which you also return at the end once you're done with it. And then this is simply the reducing function that you apply. So hopefully that makes it a bit clearer as to why folds are the way that they are and how to use them, because really when you understand how they work, you can capture a lot of behavior with very little syntax, which also makes it the rest of the code a lot clearer to read. So yeah, this is an example of how that's updated. So in this case, you know, you have a list, a starting value, and then some reducing function, and you recursively apply the reducing function to whatever value you have and some element in your list. And then that becomes, you know, 0 plus 4 becomes 4. You have that as your new accumulator. You have one less element, and you do that again. 4 plus 7 equals 11. Take it here. Still one element in your list. 11 plus 5 equals 16. List is empty. Return 16. Let's get a question. Why is the accumulator of type B while the list contains elements of type A? It's a good question. So, for example, say that you have yeah, so if the accumulator returns an element of type B, or an element of type A, then when you try to apply this function again, you don't have a B anymore, because then this would return an A, and you give that to this part right here. So then your accumulator is suddenly of type A, and then that kind of means that all b's have to be of type A, but that also means that they necessarily need to be the same. For example, it works if you're just summing integers, but say that you have a list of integers and you want to turn it into a string. So for example, you have list 1, 2, 3, and you want to turn it into the string 1, 2, 3. Then the output of this function would be a string, and of course you're starting with an empty string. So then you would write that something like list 1, 2, 3 dot fold left, start with an empty list or empty string, and then you have a lambda abstraction of your accumulator and your x. For fold right, the accumulator is to the right of x, so these will be switched around. And then you say, well, I have my accumulator, it's a string, and I'm gonna append it to this x, which is an integer, and I'm gonna cast the integer to a string. And then in this case, the specific type A and the type B are different from each other, which is a pretty desirable property, because say that you're only able to return integers that would reduce a lot of the potential behavior that you could write. So the type definition can still be a bit confusing, but I think this definition right here, if you study it a bit, it might clear it up a lot. So let's see. Right, so I have to improvise a little bit here. Yeah. So you might get something about program reasoning, which is quite easy to do, because the only thing you need to do is you find where these rules apply, and you rewrite them accordingly. You rewrite them to the right side of this equal sign. Important to know is the difference between applicative order and normal order, and I've always found it a little bit strange. I thought applicative order means you only rewrite something when it applies, and normal order is normally how you intuitively do it, but it's really just more that applicative order tries to evaluate the arguments first, and normal order is the normal way of doing it in a functional language, meaning try to calculate as less as you need. Well, actually, no, normal order is left first, the leftmost expression first. So in this case, leftmost expression is square. It'll take whatever this x is and turn it into this expression, so then it'll be, this x is negate 5, so it'll be negate 5 times negate 5. The leftmost one is this one. It'll, I think I might have messed that one up a little bit. Yeah, so this one just negates whatever this 5 is, so it'll be minus 5, and then the leftmost reducing expression is this one, and then you end up with 25. And in this case, you first do the argument negate 5 becomes negative 5, you square it, then you end up with this. So in this case, this is faster, but what might happen is that you work with some sort of an infinite type, and then trying to first calculate, for example, an infinite list. That's gonna take a while, and you're gonna run into a Stack Overflow. So in terms of the induction proof, in previous years it's been quite strict in terms of the structure that they want you to have. We had designated style points. I think it might have been something like 4 points for the base case, 6 for the induction proof, and then 6 for style or something like that, maybe 4 for style. And that was really only just for the points that you could get for, do you conduct yourself in the right way? Do you have the proper structure that you use? So I'll run you through that and highlight the bits that are important. So chances are that you'll get on the exam this line right here, all the way until proof with an F, colon, and then you have to start writing over here. then it's important that for any expression, if there are any parameters involved, then when they're introduced, you define what types they are. So in this case, we have AS and BS, and the types are defined over here. They're both lists of general type A. Then you'll always say prove by induction on, and then something that you can apply induction on. And it's important to not pick two at the same time, because that's impossible. You can't say induction on both AS and BS. So you can have a parameter defined here that you do not apply induction to. You only pick one of them. And the way that you decide is by looking at the rules that you have. So in this case, if you look here, you have AS plus plus BS. And yes, mainly just that one. So if you look at the definition of plus plus, you can see that this BS remains untouched always, but this AS can be either nil or it can be split between the head and the tail. So really, the first argument of this plus plus is the only one that you can't even apply induction to, because you don't have any rules for this second element or the second parameter. So that means that we'll do induction on AS, and an induction proof consists of two separate proofs, a base case proof and a recursive step proof. I think it's step, yeah. Then the first thing you do when you start a sub-proof is you say what your assumptions are. In this case, we assume that AS equals nil, but in general, whatever you're trying to do induction on, you want to pick the smallest value possible. So say that you're working with integers and you want it to work for every natural number, then your smallest case is 0. But say, let's see, are there any other recursive types? Yeah, strings, for example, it would be the empty string. So you try to find the smallest value for which it works. And for some proofs, you cannot use the empty lists. For example, I think it was something like the init and take proof. I think you might have done that one. That one needs at least one element, so just try to do it with the smallest value you can think of. If it doesn't work, you try to make it one larger. Then whenever, this is a separate subproof, so you repeat the line where you say, I want to prove this, which is just the exact same thing that you have over here. And then you start your proof with an F, and the first thing you do is you just copy paste that prove line. As well as in the induction step, you just take this line, put it here, and only then do you underline the part that you want to change and whatever rule you're applying, in this case, your assumption. It's important to not immediately start with, obviously AS equals nil and I have to prove this, so I'm just going to immediately rewrite it to nil. But you have to keep in mind that mathematical proofs like this have to be there needs to be no ambiguity. So when you suddenly introduce a nil here, people are going to complain where you got it. So that's why you do this first step here. And then in any subsequent lines, please don't forget this double arrow, because this indicates that these two lines between here are actually the same expression. So if you forget this, then you don't link them and your proof's invalid. Let's see, got a question. Should we use general types like A in our assumption when we need a value like where init, as you mentioned? Hold on. In that case, yes, you do need, if you need one element in your list, it's a bit ambiguous. I think you might as well just say, I have some elements in my AS small a, and it's of type big A or general A. You can, of course, infer it because an element from a list of type A is just type A, but you might as well write it just for the sake of completion. Although maybe they're just more lax this year and it won't really matter too much. Hope that answered your question. Hope I understood correctly. Yeah, so then what you do is you find some sort of you have some line, you underline what you want to change, you indicate what rule you're going to apply, and this is all just keyword going to, and then you write the resulting expression on this line here, and then at this point you can underline a new part again, indicate what rule you're applying, and so forth until you get to this part, and you can only stop if these two expressions are in fact equal to each other. I got a question. Shouldn't there also be assumption after the first line, because the step of rewriting AS to nil is also used on the right side of the equation? Let's see. That is a good point. I think it's excusable that if you apply the same rule to two different parts, that you only need to write that rule once. But if you want to be safe, you can also say that the assumption is over here. And in fact, if you want to apply different rules, then you do have to specify. So for example, if I had some way to rewrite this expression and it will be rule 5, for example, I'm not sure why this happens, then you could underline that, say here rule 5, and then rewrite this AS according to your assumption anyways. So you're allowed to do different, apply different rules, as long as they're not on the same side of the equal sign, but do keep in mind that it might make it a bit more error prone. All right. So, and also don't forget this last part. It can be QED, it can be a square, it can also be just a single period, but something to indicate that your subproof, your base case proof is done. Now, moving to the induction case, again, you start with your assumptions, and in this case, you always say assume property holds for certain whatever you're implying induction on, and then what you write here is simply the expression that you're trying to prove, and that will be your induction hypothesis indicated with the IH right here. And then what you do is, instead of saying, I want to turn AS into a head and a tail, what you did for the base case where you say assume AS equals nil, you actually immediately write the prove line here, where you make whatever you're applying induction to 1 larger. So if you're working with integers, it will be +1. If you're working with strings, it would be like ++ and then some character, I suppose. But for the case of a list, you add an element to the head. So, well, actually you add a head to the tail, I suppose. So, and again for all A, and here you actually don't have to define, apparently, what the type of A is, because it's inferred from the type of the list, but you might as well. Really, there's no reason not to, unless if you're short on time. Right, and then here again with the proof, the very first thing you do is you just again copy your prove line, and then you underline what you want to change. And the very first thing that you work towards in your induction case every single time is you want to rewrite either the left side to the left side of your induction hypothesis, which will be this one right here. So I either want to rewrite this part to this part, or you want to rewrite this part to this part, whichever one is easier. But you will have to separate this A from whatever is in here. As you can see here, in the case of when you're applying recursion on lists, you'll always have your main expression be some split between a head and a tail. And then the tail is where you can apply your induction hypothesis. So if you do your induction proof or your induction case proof, and you somehow get to the right result, but you never use your induction hypothesis, that's wrong. There's just no way. You'd need to use your induction hypothesis. So the very first step you try to do is you try to separate this head from the list in order to get this expression to be the same as this one. You can also do it with the right side, of course, whichever one's easier. And I actually think that I forgot the QED here, so don't do that. Because that's for the induction case proof itself, the subproof. And then for the larger proof, you say, well, I have my base plus induction proof complete. I'm not sure if they're going to be strict on style points, but if they are strict, then this is something you can also lose points on. And again, don't forget the arrows. So this is something I naturally didn't copy from my previous presentation, which is the new way of doing overloading. And this is something that I'm pretty sure a lot of you have trouble with. The others I'm not too sure about, because I think at least currying, as far as I've seen, isn't causing as much trouble as it did in previous years. But overloading is certainly quite confusing. So I'm going to run you through the parts, how it's made up, and why it works as it does. So we begin by introducing, let's see. Oh yeah, good point. A break. I totally forgot, you're right. Yeah, let's have a break of 15 minutes. I'll be back at, let me make it 14 minutes. So I'll be back at 5 minutes past 12. All right, I think I'm back. Just gonna send a message in the chat to make sure that people can actually hear me. Good. All right. I'm gonna wait a few minutes for people to rejoin, just in case they're doing something else. Yeah, you guys can ask some questions in the meantime. I don't really have anything planned for these probably 2 minutes I'm gonna wait. Oh, was my camera covering some of the slides, by the way? Guess it might. Yeah. All right, that's fine. I'll upload them. All right, let's continue. So what will be nice for overloading is if we wouldn't have to use all of this implicit stuff. So I'm just gonna write some pseudocode that doesn't work at all, just so you can kind of understand the intuition behind this. Let's just go here. So say that you would have something like say you have a function called equals. We're just going to make a function called equals. Def equals has some general type A, and the type definition is it takes some x of A and it takes a y of A, and then it returns a boolean indicating if they are the same or not. And then that would really be it. Then you don't make the type definition. And then what would be nice is if you could do something like override def equals for integers, where you take an x of an integer and you take a y of an integer, and then you return a boolean again. And then here is where you make your implementation, where you just say x equals y. So as you can see, this doesn't actually work, but it might have been nice if it did, because then you can also write override equals for float, for example, and then you could do something like println equals, and then you give a 3 and a 4, and it'll return false, where it'll find this definition of equals. It'll look for something where the arguments are of the right type. So in this case, the arguments are integers. So then it'll find this one, and it'll execute this part. Now, the equals is already overloaded, so that's why these aren't different. But technically, overloading allows you to define a single function that works for different types. For example, something that they have in Haskell, which I still don't understand, is you have 2 division functions. So you can write something like 2 divided by 3. And I believe that would give you a float, but then you also have the function div, but then div isn't infix, so you would write it like div23, and then this would give you an integer. But if you want to make it infix, then you have to do it manually, and you say this. And it's a bit the same with, say that you have 3 plus 4, but then when you're working with floats, then you have to use a different function. I don't know, say plus plus, and you say 4.0f, and you need to write something different here because there are different types, and then you cannot use this one for lists anymore, and you end up with 20 different functions with pluses. So that's why it's nice to be able to define a function that works on different types, and the way that that is implemented in Scala is mainly by the use of implicits. So let's go over that. So here, this would be our equals, our general definition of equals. The backticks, that's not Scala syntax, that's Haskell syntax. It basically, if you have a function that takes 2 arguments with the backticks, you can turn it into an infix operator. But that's Haskell syntax. Right, so in this case, the trait named is our general definition for equals, where we don't give an implementation. As we see here, there's no equal sign. Yeah, and we give it some method that it contains called nameOf, and it takes a single parameter, takes some x of type A, the same type as we have here, and it outputs a string. And the idea behind nameOf is it will give a string representation of the type of this A and the value of this A. So it doesn't do anything fancy, it just returns a string so you know what this is. And instead of being able to directly overwrite this, we actually define an implicit class that extends whatever this is. So yeah, so basically we say here, well, we have some class, it takes some parameter. This would be in the same sense that if you have a list you can call .map, then you would write something like implicit class list ops, and then you have, some list. This argument would be of type list of A, and then in this definition somewhere here there would be def map, and then it takes some arguments, or it takes one argument actually in this case. So that's why you're able to just use or just call methods with a period. It's because those definitions are defined in some class that extends this type. So for example, say, I'm not even sure if this works, but we'll see. So let's say implicit class, let's see, extend int, and then it takes some argument, some x, or let's say an n of type int. Then we just do this, and then we say def nameOf, and then that's it. And then we say, well, let's say it's an integer, and the value is x.toString. Oh, it should be n. So type annotation, right. So now we've actually extended the integer class with an extra method. So I'm pretty sure that we can do something like println, and then we say 5.nameOf. And then if we run this, I hope, yeah. So with this syntax, you're basically able to add some methods to whatever class you want to add a method to. And with this syntax right here, instead of saying, well, we want to use it for integers specifically, is we say we want these methods to be available for any type that has the trait named defined. So then say that we define it for integers. So this is the syntax that we use. We use an implicit value, we give it some name. This name doesn't really matter too much. What matters is the type of this value. And then for some reason you have to say new and then the same type. Then you open it and then you override all of the methods that are in that trait. In this case, it's just nameOf, and keep in mind that this nameOf function is in fact different from this nameOf function, because this one takes a single argument and this one takes nothing. Something you might have noticed in the assignment as well, where you have in this case you have fmap. The thing that you're overriding is fmap, but the method in the class is actually called map. So that indicates that they are in fact not the same function. Not necessarily, but you can call them the same. Chances are they will take different arguments though. So if we override this, we can say, well, if this is an integer, then we know that the type is an integer, and we also want to print whatever the value of that integer is. So this is our implementation for named of type integer. And then with this class, if we have some value and named is defined for it, then we say, well, it includes this extra method. It's extended by this method. And this is where some of the magic is involved. The key to why this even works, why we can use this function with different types, is this implicitly. Because what this implicitly does is essentially you give it some type and it tries to find some implicit value of that type. So let's see what happens then if we call something like this. So we have an extra function which gets some general type A. We don't know what it is. Could be an integer, could be a string, could be a float. The only thing that we know is that it has the trait named defined. And we get some parameter of type A, and it outputs a string. Then we just call x.nameOf. So this is just something like a wrapper around it to make sure that it works with any type A for which named is defined. And then we call getNameOf. This should be int. Just imagine that these two functions are the same. So then when we call this, what essentially happens is it notices that whatever this type is, it has name defined. So the methods included in this this parameter are at least just nameOf. So then, and this is kind of a big step, I always think. So you can kind of see it as that this this x gets called with nameOf, but this doesn't always work. So you might need to do this, where you say, well, I have this class named ops. I give it some parameter. In this case, it's a 5, so that's of type integer instead of a. So then this a becomes an integer here, and it also becomes an integer here. And then what we do, well, we have this class. We call the function nameOf, and then what that expression turns into is this thing right here. So then instead of that, we get this. And again, the general type A is substituted by the type int. So now we end up with this expression. And as I said before, the implicitly function takes some type and it tries to find an implicit value of that type somewhere in your code. And the only one that it's able to find is this named int, because again here, the type is named of int. So then this implicitly named of int is substituted by this named int over here, like this. You see how name of 5 is still the same, but this is substituted by something else. And now we know that, well, we have the value named int, and it contains some method called nameOf, and that's what we call with the parameter 5, which is an integer, which is correct. So then that whole expression is substituted by int colon plus plus 5.to string, and you get this as a result. So those are the inner workings of using implicits for overloading. But intuitively, really the only thing that you might have to work with on the exam, I'm not sure if you actually have to define a class like this. You had to in one of the exercises, but you might just get both of these, and the only thing you're asked is, well, define this trait named, in this case, for some value, whether it's an integer, a float, a string, or a character, or maybe something they've defined themselves, like a person or a parent. So particularly this syntax and how it relates with this trait syntax here is important. And then if you actually want to use these functions, you have to make sure that you understand this, because when you call name of, you're not invoking this function, nor are you invoking this function, you're invoking this function, and then it will find this name of function for you. So that's, you call it with name of without any parameters, so that's this one. All right, so yeah, that's all I had in terms of the presentation. So I'm going to look at the poll results now. Let's see. Okay, so there's not a significant amount of difference, I suppose, maybe because actually, it's still changing. I'm going to let people vote a little bit more. I posted the link in both text chats. Yeah, so far it looks like there's really not a lot of preference for either. It's kind of the same amount for all of them. All right, I think there's a slight preference for rewriting another exam, but I think what I want to do first is actually go through the one that I've already done, because I've done some of the exercises there already, so I can get that done a lot faster than rewriting another exam, but chances are I might do that anyways as well. I'll just take the exam that I've done previously and then go through the most important questions. Let's see. So that's this one. I'm going to skip this function because really the only thing that this... Actually, let's get the actual exam PDF and then I'll drop it in the Google Drive folder. Yep. All right, it's uploaded in the folder. I gave you guys some time to download and open it. I think in the meantime, I'll just... was that right? Yeah. Yeah, so the first one I'm not going to cover extensively. It's quite simple, really. There's just a table that you get for if you have parents of a certain blood type, what possible blood types are there for their child. And of course, because there are 4 blood types and 2 parents, you have 4 times 4 equals 16 possible combinations. And you could hard code all 16 possible combinations, which I would be very sad about seeing because it's very inefficient and it takes a lot of time on the exam, but it works and it's correct, so that's full points. So that's fine. Yeah, there's an example solution there that you should be able, like it shouldn't be too hard to translate that to Scala syntax, really. I don't think I'm going to cover this either. Type definition should be found in the example answers as well. So yeah, let's head to question 3 then. So this is actually about overloading, so that's good, we just did that. Now, we have some general function that we want to apply called blood of, and it's included in this trait called blood type. So you have this function blood of, it takes some argument of type A and then it returns a blood. And you want to return this, or you want to implement this for different specific types. Then we have this implicit class blood of, which is necessary so you can do the whole, whatever your parameter is, dot blood of, and you get the value without having to explicitly write this. So in the case of blood of blood, we see that this is a blood type of type blood, and this should override this. And the first thing that we do, of course, is new blood type of blood, which is necessary. Open brackets, and then we override whatever methods are contained in that trait. So in this case, that would be override def blood of, and then this A, this general type A, is substituted by this blood. So in this case, the type of X isn't A at all, it's blood. So that's X of type blood, and the output is still, as it says here, just of type blood again. So if you think about it, how many ways are there to get a blood from a blood? Well, really there's just only one, and that's returning the same thing. So that one's pretty simple. Also because aside from, that it's one of these four, you don't know anything about blood. I suppose you could just be a bit cheeky and hard-coded and say, it's always A, but of course that would be wrong. So A being, of course, the blood type A, like AB, and not general type A. So if you go to blood of info, then we have to look at, well, what exactly is an info. And we see that the type info is defined, don't look here, look at whatever the first one is to the left of the equal sign. So in this case, info is defined as a class, and it has, or an algebraic type with two parameters, a name and a blood. And these fields we can just call with a period. So obviously, if we have an info and we want to get a blood out of this info, we can just call whatever that parameter is dot blood. So in this case, we do the same thing. So that's, I'm not sure why this is convert. Sorry. Let's see. Huh. Okay. I didn't know you could do that. Well, let's do new blood type of info, because that's what we have to do now. Then open brackets, you override whatever is in that trait. So that's override def blood of, and you take an X, in this case of type info, and you say, well, an info contains a field blood of type blood, so we just do this. And then in the case of person, really quickly, I'm not going to write the whole thing because I think you get the idea now, but in the case of person, a person has a field info, and again, an info has a blood. So we can write something like, just going to very quickly just copy paste this. Person, and then like that. So you first take the info, then you take the blood. Yep. And in the case of spouse, it's actually the same. They also have a field of type info, so you just do the same thing that you did with a person. Now, in the case of not biological parents, what this function does is it takes some tuple of A's and it takes another argument also of type A, and we don't know anything about this A because it's a general type. But what we do know is that it has blood type defined for it. So what does that give us? Well, if we look at blood type, then we have one implicit class that extends the methods of this of some blood type. So what we have available to us is blood of, which is a function that returns the blood of whatever that A is. So that's all we have available in terms of manipulating our arguments. And what this wants to know, or it wants us to write, is some function that takes some representation of the blood types of the parents, in this case as a tuple of A, and it takes some parameter that's a representation of the blood type of the child, and all it wants to know is can this child be a biological child of these parents, for which we would use the child bloods function, which we didn't implement. So let's just assume that it works. Let's just have this return a dummy value list of just A, or let's do AB. So of course that doesn't work as it should, but it will do its job fine as a dummy value. So in this case, we look at the function that we definitely want to call, which is child bloods, and it takes a tuple of bloods, and then it returns a list of possible blood types for the child. But again, we don't have a tuple of bloods, we have a tuple of A's for which blood is, or a blood type is defined, the trait. And with that trait, we have the function blood of, which will give us a blood. So that's exactly what we need. We need two bloods. So what we can do is we can first, what I recommend is writing the parts of the function that you know should be in there, and then only later on figuring out how do I combine these into a proper expression. So we definitely know that we have to change the types, or we have to turn this tuple of A's into a tuple of bloods. So what we can call is ps._1, which will give us the first A, and then we can call blood of, which will turn that A into a blood. And then we can do the same thing for parents._2 blood of, and then we have two bloods. And if we look at the function child bloods, it takes a tuple of bloods. So, well, quite obviously if we have to put it in a tuple. And now we pass this tuple, because now we have a tuple of bloods, to the child bloods function. Yeah, and of course some extra brackets to indicate that it is a single argument as a tuple. And now, as it correctly says, we have a list of bloods, but we want a Boolean. And what this Boolean should represent is, can the blood type of this child be a result of these parents? So really the only thing we have to do is turn that C also into a blood. So now we have some blood, and we have two expressions. We have a list of bloods, and we have a single blood, and we want to turn it into a Boolean. And well, essentially we want to check if that blood is in that list. So what we can do is dot contains, and that's almost it, because what it's supposed to do is it's supposed to check if they're not biological parents. So then this would only be true if the child is not contained in that list of bloods. So then we simply negate it. And now let's see, all parent child parents. That's a good one. Yeah. So this is a pretty good example of a very sneaky trick that might be helpful in the exam as well. We're going to use list comprehensions. So we're going to start with a for, and we're going to take something out of this. And well, you want to do a for comprehension on a list, and well, we have a person, so let's see how we get. Oh yeah, I'll first explain what the function does. Maybe that's a good idea. So basically what this wants is, if you look at the definition of a person has a field spouses, which is a list of type spouse. And a single spouse has a field called children, which is a list of persons. And what it essentially wants is, assuming that you have some person P and say that it's a monogamous relationship, then it'll be just a single spouse. And they might have multiple children. Then say that you have, just going to write it here. So that you have a person P1 and a spouse S1, and they have children C1, C2, and C3. Then the resulting list that you want is, let's look at the type, a list of tuples of parents and child. So let's just copy this. Let's put it here. And if we look at the definition of the type parents, we can see that it's defined as a tuple of two infos. So really what this says is, okay, well, it's a list of tuples where the first element of the tuple is another tuple. And then if we look at the definition of the type child, we can see that child is also defined as an info. So really this just says that it's a list of these types. And then the resulting list that you want is all possible combinations of the person, their spouses, and their children. So in this case, P1 just has a single spouse S1, so the resulting list, going to use shorthand syntax again, would then be something like P1, S1, and then C1. And that's one element. And then we have it again for the different children. But then now say that P1 is actually, I think the right phrase is polyamorous, probably. So P1 has two spouses. So then what happens then is the number of possible combinations doubles, because there's, well, these children would be of spouse 1, and maybe spouse 2 has two children. Let's call it C5 and C6. And then it will be something like, you know, P1 and the second spouse, and then C5. And P1 and the second spouse, and C6, and that's where it ends. So it's basically just all possible combinations of the person, their spouses, and the spouses' children. And that might seem like a very big task, because you're essentially doing a double for loop, because you're looping over the spouses first and then the children of those spouses. But there's a very sneaky way that you can use a for comprehension to abstract away from this. And you can do that by saying, well, I want to get some spouse of the spouses of P, and then I want to combine it. And this is something that a lot of people don't know, that you can actually use this S over here. So you can say, well, I want to get all of the children from s.children. And now say that you say, well, I just want to yield the C, which returns an error, because of course this is a list of person, because the list of children is defined as a list of persons, so a single C is a person. But this would then essentially return all the children of this person, because you're kind of unfolding the children from the list of spouses. But in fact, you don't want a single child, you want to have elements of this type. So whatever is here should be of that type. And we know that the parents is defined as a tuple of info. So let's just put those parents here right now. We take the P and we take that spouse, because this is something that you return for every possible combination of these. And the child is C. But this also doesn't work, because we don't want a tuple of person, spouse, and then another person. We want infos. So if we look at the type person and spouse, again, we can just see that they have a field called info of type info. So then we can just call dot info on both of these, or actually all three of these. And then this is almost it. I think, because what we actually want to know is we've just done it for this person P right now. So if there's a single person and they have a number of spouses and the spouses have a number of children, that's essentially just one layer. But we also want to do it for the parents, or I suppose no, we also want to do it for lower depths of that ancestry tree. So what we want to happen is we want to somehow recursively call this function. So let's do the same thing and say, well, we're going to write it on a different line. We'll see how to combine it later on. So then if you want to recursively apply it, then you somehow need to find a way to generate one or multiple or none new persons from this person. And as we've seen before, when we did this, then it returned a list of person, which isn't too strange because these are the children of that person P, and a child is just defined as another person. So we can actually use this whole list comprehension again to get all of the children of P. And now that we have the list of children of P, the type of this whole thing is a list of persons. And if you want to recursively apply all parents child pairs, you need a single person. So we can either say, well, we can do a map, but well, we have access to a single person right here. So you might as well just say, I have this child and I want to recursively apply this function. So I'm just going to do it here. All parent child pairs on C. And then instead of a list of children, you get a list of whatever this is. Because this is the output type of that function. But then you get to another issue, and that's, well, I want a list of tuples of parents and child, but with this expression I have a list of lists of parents and child because I'm performing this function for every element in some list. And this is exactly what I was talking about in that available functions part of the slides. If you need some list of a certain order and you have a list of an order but higher, chances are you just have to call flatten and that's it. And now there's another issue again, of course, because we just wrote these two separate expressions, but in a functional language you need a single output, so we have to somehow combine these two. And we've just ensured that we've reduced the order of this list by 1. So now the type of this expression right here is this, and the type of that expression right there is also this. Ignore the syntax errors real quick. Yeah, let's do it with a comment. That's a wrong type of comment. So, and this is a bit akin to that flatten thing where, say that you have two lists and they're of the same type, and you want to, first of all, not discard any of the information in each list, because this is important, but this is also important. So if you have two lists of the same type and you want a single list of that same type, you really don't have that many options aside from simply concatenating them. And this is, you know, the whole part with the flatten and the plus plus. I'm not sure why this doesn't work. Maybe it's because of this. No, maybe it's because of this. Yep. So this whole reasoning about the flatten and the plus plus wasn't even done in the implementational level, where you think, okay, well, we have this whole list comprehension here. What does it do? What sort of values can we get out of it? The only thing we really reasoned about were, well, what is the type of this expression and how can I make sure that it turns into this. And that's really a much simpler space to think about. So if you're ever stuck in an exercise, the first thing you should really do is think, okay, well, what types do I have here? How can I apply that knowledge to the other things I still have to fill in? And what expressions do I know I definitely need? And then you can think, okay, well, how can I take the types of these expressions and turn it into the type that I need? And then someone's running up a question, so I'm going to wait a little bit with continuing. Let's see, do we need to do the loop, do the for loop again, or can we just do ++ all parent child pairs C flatten? That's a good question. Let's see. Oh, maybe you're right. I suppose you're right. I didn't see that. Yeah, so let's try that. So let's do ++ all parent child pairs, and then we do but then it should be in a for loop, so we do something like oh, hold on. Yeah, no, I see what the issue is. The issue is that you need to take the C from somewhere. And if you just have a person and you want to do it for every child of that person, then you do need to do something like this to get access to those children. But it's a good idea. Right. So for all not biological parents-child pairs, which is quite a mouthful, the implementation of this function is actually quite simple, assuming that you have the previous two functions. So we have if you look at the types, we have a single parameter of type person, and it should output a list of parents and child, and we have a function that does exactly that called all parent child pairs. So let's just use that one, because chances are we're going to need that one at some point anyways. And let's just give it, well, it needs a person, so let's give it a person. And now we've actually already achieved the requirement of the type needing to be correct. Let's do this a little bit more. But again, this doesn't really do what it's supposed to do, because it only wants the parents-child pairs that are not biological parents. So then chances are we're going to have to use this function somehow. And if we want to remove elements from a list but keep the types of the elements the same, 9 out of 10 times you're going to use a filter. So let's start writing that. So dot filter, and then it takes a function, and it should, why is that not working? Okay, well, it takes some argument and it should return a boolean. That's what you do with a filter. Strange. Whatever, let's just roll with it. So this takes some element out of your list, so that will be a tuple of parents and child, because that's what it returns. So let's just paste the types here to make it easier to see. Parents again is a tuple of info and info. So that will be something like parent 1 info, parent 1 info, yeah, parent 2 info, and then child info. I'm not sure why it is complaining. Dot, come on. Filter. Yeah, well, the types seem to line up. That's strange. Okay, well, maybe that's just because this isn't done yet, or maybe it's because of these things right here. We'll see. So we want to filter based on these not biological parents function, and the type that it takes is, well, it takes some tuple of A for which blood type is defined, and it takes another argument C also of type A for which blood type is defined. And we have a list of, well, all of these are infos, and we actually do have info defined for blood type. So that means that we can simply pass those infos. So in that case, we actually don't need to unpack this as a tuple at all, because it already takes a tuple. So let's just call it PS and then C. And then we can say, well, we're going to filter on not biological parents, where we give that tuple PS and the child. And I'm not sure why this is complaining. Hello. All right, well, let's just assume that it works. I don't know, it doesn't show an error, so actually, hold on. What about this? Brackets around single line expression, I suppose. Well, that didn't fix it. Okay, well, let's just assume that it works. It's probably just a minor optimization. If you would do something like this in the exam and it doesn't work in an IDE, it doesn't matter, as long as we can see that, you know, the intuition's there, the intent is there. Yeah, so I think it's almost time for a break again. So yeah, we're gonna have a break in a bit. I'm gonna make this one public so you can fiddle with it yourself. Bloodline is actually a pretty tough function, so I think that would be a good good exercise. There's some very minimal starts to an induction proof over here, and then when I get back, I'll just open the floor to questions or requests. So I'll see you guys in a bit. And let's say, 15 minutes again. So that would be 8 past. All right. All right, I'm back. Just checking if you guys can hear me again. I'm gonna spend those 2 to 3 minutes. I'm gonna wait for people on trying to figure out why this doesn't work. I'll see. You guys can hear me though, right? All right, good. Let's get a... Yeah, if you want to do this practice exam, then an association list is pretty important. So I'm just quickly going to write the add function. That's at least the one you need. Okay, so nil. Yeah, I'll also upload the Scala files. Actually, everything that's in here, so there's an extra exercise here, which we did last year, but not this year, where I might go over this one real quick. Yeah, so these are this essentially encodes playing cards. So you have a suit, you know, hearts, diamonds, spades, clubs, and you have a value, ace, king, queen, jack, and some number between 2 and 10, which is implied, but it could also be negative if you want to fuck with it a little bit. Can I say that on Twitch? I'm not sure. Yeah, so then this is just some stuff to make it easier to work with. For example, you can give the function handify a string, and it'll say 5 of clubs, 2 of hearts, jack of spades, 8 of clubs, and king of hearts, and then it'll give you a list of cards. And then these functions are essentially, well, write functions that can take a list of cards and then return a boolean indicating whether or not this hand of cards is a high card, or there's a single pair in it, or there are 2 pairs, or 3 of a kind. There's one for flush, there's one for straight flush, and royal straight flush. And what I would recommend is writing a function called inspect that, let's take something like this. 5, I actually want to have some duplicates in here, that would be nice. So let's make it 3 of a kind. So we'll say 5 and 5. So an example input to this function would be something like inspect, handify, and then the output would be yeah, so that will be a list of 3, or let's do 1, 1, 3, indicating that there are 3 values of one kind, in this case the 5. There is 1 value of another kind, for example, the 2, and then there's another one also of one kind, for example, the king. So this would be a function that I would recommend to write instead of doing these manually, because what you can then do is say something like, well, if I have a full house, then and I have this hand, then I can do inspect on hand, and if it's a full house, then the only possible thing that I should get from that inspect is a list of 2, 3, indicating that there are 3 of one kind and 2 of another. So I'll upload that one as well. But yeah, I'm just gonna open the floor to some questions or requests. So feel free to bombard me. I suppose you can also try to sort of raise your hand in text if you're afraid of talking over each other. But go ahead. There are no specific requests, because then I might just do some stuff with currying, because that was a request. All right, I'll do that then. So let's get this one. Use a simple example. So say that, and we'll keep this one here, might as well. So the idea behind currying is that it allows for something called partial application. So because you're in functional programming only writing expressions, there, as they say, there are no side effects to your program. So the only thing that it really does is it outputs a value. It doesn't retrieve some variable, change it, and then put it back. So because you're essentially only working with expressions, you can do some syntax that simply works because you're only substituting expressions with each other. So in the case of calling a function, if you want the function to give a certain output, then you need to give it all of its arguments. But what you can do is you can essentially construct a new function from an old function by only giving it part of its arguments. So let's do something that was in the exercise as well. Def add, it takes an x of an integer, capital I, and it takes a y also of an integer, and the definition is just x plus y. So I need to do this because the plus is an infix operator, and I can sort of curry it with, let's say, val xs equals list 1, 2, 3, and then I do something like xs.map. And then, for example, I could say underscore plus 1, and then the resulting list would be 2, 3, 4, because it applies this function to every element in that list, where it fills in that element at the place of this underscore. This also makes it that currying, unless if this would be considered currying, that it doesn't seem all too necessary in Scala, so far as I've seen, because you can just use this. These underscores are pretty nice, I gotta admit. But what you might, so the reason that you have to write these separately is, say that you only want to give, say you want to call add, and it just takes its arguments like this, and then you want to add whatever x you have to, you want to add 1 to whatever x you have, and you could say like add 1, and then I don't know, I'll finish the parentheses later, which obviously isn't really allowed. Let's get rid of the print. Actually, let's do this instead. You know, this bracket here would actually belong to this map here, so you need to give it in different parameter lists. In this case, they're just singleton. Well, maybe list is a bit confusing. Yeah, but if you write this, you can say, well, I'm gonna call add, and I'm gonna give it the first argument, and then the second one I'm gonna omit. And what essentially happens then is, normally add is a function that goes from an integer, takes another integer, and it returns an integer. And this is syntax that's familiar to people that programmed in Haskell. The reason that this works is essentially because it's right associative. And then what this really says is, okay, well, add is a function. It takes an integer, and it returns a new function. And that function also takes an integer. And then the result of that last function is finally a single integer. And this also shows why currying works, because essentially if you give a function its first argument, it will just give you a function that takes another argument. In this case, if you give add its x, then what you get out is this. So then if you say add 1, then the type of that is simply a function from integer to integer, because you've already given it that single integer, meaning that it can give you whatever's at the right side of the arrow. So in that sense, what this actually ends up, like in terms of what sort of expression this ends up being, is, let's say, let's put it in comments. So this is the same as, you know, you expand this list, this XS, so that would be this dot map. And then for the definition of map, essentially what, you know, you have, let's just define map here, might as well. Def map takes, yeah, this is not actually how it's defined, of course, because you call dot map, so this doesn't work. But I mean, this should give you the intuition of how it works. So you get a function from an A to a B, and I have to indicate that B is a general type as well. And then it gives you a list of B's. So in this case, the function that you give to it is one that takes a single argument and gives you a single argument. So using add wouldn't work because it takes two arguments. But what you can do is you can already give it one of its arguments, then it needs one less, and then you turn it into a function that only takes a single argument. So in that sense, what this actually says, because it applies whatever this function is to each element, is a list where you say, I have the function add 1. That is the whole function that you give to it, because you pass it over here. And then you apply that to, you know, you do the brackets as if you're just calling a regular function, and you give it the first element of that list. And then you do the same thing there, but instead of calling it on the first element, which is a 1, you call it on the second element, which is a 2. So you can kind of see this thing itself as just another function, just one that takes a single argument instead of two arguments. And then of course the same thing happens for the last element, which is a 3. The reason why this is normally very useful for purely functional languages is because you're very close to the expressions in the foundation. But in Scala, you have some shorthand syntax with, for example, that, you know, underscore and then whatever, and you fill in your parameters. So currying seems to not be as important here. But if you can understand why you can define a function like this, then you should be able to understand why why you can curry. For example, let's make a different function, call it add3, and instead of adding 2 numbers, it'll add 3 numbers. So it'll add a z of type integer. And then instead of it taking a single integer, returning a function that takes another integer, and then returning your result, it takes an extra step. So actually, after it takes the x, it'll take the y, but then it still needs the z. So then this is another function that takes an integer and returns a new integer. And of course, this one can also be curried because you can give it this one, at which point is a function that still takes 2 arguments. But then afterwards, you can also give the second one, at which point it's again a function that takes a second argument. So then you could do something like add 3, 1, and 4, for example. And then you add 1 plus 4 plus whatever element this is. Yeah. So does anyone else have any specific subjects that they want some extra examples for, or another explanation? Because otherwise I might just run you guys through either this poker hands thing, or I'll just rewrite that exam. I got a question. What happens when you give @3 only one value? It's a good question. In that case, it doesn't actually work with math, but what we can do is we can actually do this with a fold. So let's change this to an add and a 1, and let's change the 1 to a 5 actually, otherwise it might conflict with this. And then I'll change it here as well. And here. So let's say that we're doing a fold, and we want the fold to just add a list of numbers to each other. Let's just take XS in again. So then we call XS.fold. Let's do fold left. Fold right's more efficient technically, but I think fold left is easier to understand because it has the same structure as a list. The first thing that it takes is a starting value. In this case, that will be 0 because we want to take the sum. And then as a reducing function, what you could technically do is you could say, well, I'm going to do add. Not sure why this doesn't work. It might be because it's, because it's curried, that's why. Yeah, because if you do something like, do something like this, accumulator, comma x, turn it into a lambda abstraction or expression, and you say add accumulator and x, this will work. So actually what we want to do is, say that we wanted to use add directly, then we'd have to uncurry this, which is also kind of a pain why you would constantly need to do this. But say that we just give one argument and then we want the rest to be like this. So then this type definition changes from this into this. Don't be confused by the brackets. This isn't a tuple, it's just to indicate that they're 2 different parameters. If we were to do this, then we could say, well, we're going to add 3. So not only do we want to add all of these elements, we also want to add an extra 2 for every element. And then what will happen is something like, let's see, so that'll be 2 plus 0 plus 1 in this case, because we start with this starting value this is the thing that we always add to the reducing function. This is the starting value that we have at first, and this is the first element from our list, and then the resulting list is just 2, 3 left. And then if we do this again, the result of this is obviously 3, so then our starting value becomes 3. We always add this 2, and then we take the 2 from this list. So then there's just a 3 left, and this is then obviously 7. And then we can do the same thing again, but instead of a 3 we have a 7 now. We always add the 2, and then we have another 3, so then this is 12, and that is the end result, because now we have a nil. So yeah, if we would have kept, just gonna do it like this. If we would have kept it like this, then giving a single argument to add 3 will turn it into a function that only still takes 2. I got another question. Why is fold right more efficient than fold left? Also a good question. It's because of lazy evaluation, essentially. Because what you might have noticed with fold left, if we go back to the presentation, the point at which you actually return a value is only in the case that you've gone through your entire list, so that there's no more elements left. In the case that you can still take elements out of it, you simply call fold left again. But this is, until you get to this end result, you don't actually get access to the accumulator. But what happens in fold right, if I'm going to make a pseudo definition of fold right, so that'll be fold right, it takes excess of type list of A. I'm going to need general types A and B. Let's make it curried, because why not? Then it takes a starting value or an accumulator of type B, and it takes some reducing function or operator that gets a, in this case, an A comma B instead of a B comma A, because for fold right we put the accumulator on the right side, and then it outputs a new B, so it can update the accumulator, and again the accumulator is on the right side, so it's that B over here. And then the output of this function as a whole is B, because at some point it's going to return the accumulator. So now let's do XS match again. And in the case that we have nil, then obviously we return the accumulator just like last time. We have to put a case here. But in the case that you can split it between the head and the tail, we might have a bit of a conundrum because of the way that the operator works. So yeah, you might think, oh, we just do the same thing, but we flip these values. But what you actually want to do is you want to apply that reducing function directly, and then one of its arguments is going to be that element from the list, in this case x of type A, which we give to the left side because the operator takes the element of type, or the argument of type A, to the left. So that will be this. And then the second argument that it gets is the output of that fold right. And here we give it the tail, and remember this XS is not the same as this one. It's actually the same as this one because this definition of XS is deeper, so it shadows it. And then we give the same accumulator, actually, because the part at which we apply this operator to the accumulator is actually right here. And then we again just give the reducing function. And the reason that this is more efficient is because instead of a immediate recursive call to the function, we instead use this reducing function, and this means that depending on what the reducing function does, sometimes we might be able to just skip this whole recursive step. Because if the output of that operator is, for example, say that the operator is the head of some list, or like you have this fold and you take the head of it, and then with the operator you would return a list. But with this way, the operator can immediately return elements from your list, and by calling head, you don't need to calculate the tail at all. So that's why fold right tends to be more efficient. But I also think it tends to use more memory just because it needs to keep track of this extended expression. Let's give an example of something that could be reduced. So that would be fold right a list of what can we do with fold right? Let's see. Let's give it 1, 2, 3 again. We'll use Lambda Abstraction. It takes an X and accumulator because it's switched around now, and it says, well, I have this accumulator, and I want to append it to x.toString, and then the starting value is an empty string, or actually a list. Actually, let's do it like this. We can make it an empty string, and then we can just say that the accumulator is to the right. So then we say x.toString plus accumulator. So then the accumulator would be a string, as we've defined here, because this is the starting value of the accumulator. And then we add x to that accumulator, but only after turning it into a string. And then if we were to do dot head, then this expression would turn into something like this, because we can apply these rules here. So then it would essentially just be this operator. So in that sense, it would be let's see, let's do it like this. So then this is the function that we call on the arguments. Well, maybe that's a bit confusing. Let's just say that the x is the 1 and the accumulator is the empty string. And then it will be 1.toString plus the empty string. Yeah. Actually, this is a bad example. Yeah, but anyway, the idea is that depending on what reducing function you use, sometimes you don't need to go through the entire fold to get the result that you want. It's the idea behind lazy evaluation. Yeah. So I think I'm gonna keep maybe rewriting that exam just until it's over. I think it'll be over. Yeah, it should be over at 3. Not sure why this doesn't work. What about implicit class? Strange. Oh, right. It returns a list of K and V, but feel free to ask more questions if you have any. I'm just going to rewrite some parts of this exam, then upload it. So we have another one. Let's do value of K. It returns a V, and then we do something like this as well. of key. Actually, we can just turn this into an underscore. Yeah. And then, yeah, so the idea behind an association, let's just explain it real quick. Might be useful from the exam or the practice exam, is that it's basically a list of tuples of two general types. For example, say that it's the k is an integer and the v is a string. That you can kind of see it as a dictionary in a way, in the sense that you have a unique key for everything. So if it's a list of tuples of integers and strings, then every integer will only be in there at most once. So, you know, you can have the keys 1, 3, 5, 6, but there's no way it's going to be 1, 1, 2, 2, 3, 3, whatever. It's going to be unique keys. So then this is why you only interact with it with the add. Because if you say, well, I want to, or actually it should be update. So update finds the correct key and then returns, or it finds the correct key that you're looking for. And then it updates the value associated with that key to whatever value you pass it to the update function. And then value of, it gets a key and it tells you the value of that key. And I'm curious if you guys can see an issue already with the update function. Because say that, you know, you have say that you have a keys of, let's see, I got a question. Do you want to explain exercise 3 of our example exam with fold right and fold left? The official one, I assume, right? Let's see. Let's see. Yeah. Ah, yeah. Yeah, that's a good one. Yeah, so I'm gonna go to main. So in this case, we have, let's see, concat, concat age. So I'm just going to copy the type so that everything lines up, and then I'm going to leave the implementations out. So that's def h. Let's see. And then it outputs a list of C. Yeah. General type A. It tends to be common practice, at least in functional languages, to have the number of S's be equal to the rank or magnitude of the list. So that's why you know, when you split between the tail and the head, you say x double colon xs to indicate that x is some value of type A, and the xs is a list of that type A to indicate that, you know, there are multiple x's. So that's why I personally choose to, you know, since this is a list of A's and the defining identifier is A, then I would call it ASS. but I can understand why they wouldn't put that in the example exam. So yeah, BS list of A, and then it outputs a new list of A. And I forgot a bracket here. Are those all the ones that I need? Yeah, in terms of types, that's correct. So now we can move on to exercise 3. So that's 3 example exam. Let's put that earlier. Let's put it here. So then concats. Okay. Yeah, so we have the definitions of the folds, and actually they're the same way that I wrote them previously, with just the list as an argument. The pop filter is a little bit in the way. Yeah, so I'm just going to copy those definitions to illustrate my point. And we're going to use a let's just use a fold left. I think that's a bit more intuitive. So I'm just going to write the fold left. Why am I doing this? I already wrote it previously, I'm pretty sure. Did I? Let's just copy this one. A access match. Oh, right, it's in the slides, that's why. And now we even have a working fold left. So if you go to, let's see, concats, it takes a general type T. Then it takes a list where the type is quite nested. So it's a list of lists of lists of A. And that's the only parameter that it takes. Actually, I mean it's T. And then the output is a list of T. Now, if you remember what I said, you might think, oh, well, the order is just one larger than what I need, so I'm going to call dot flatten. Not exactly what you want to do, but I think the intuition's sort of correct. But of course, you want to do it with a fold. So let's just start with fold left. And then if we call this, we can see that if we only use fold left, then they essentially force you to have the output type of fold left be the same as the output type of the whole function. You know, if you're just using a fold, then you're equating the two functions to each other, and the types need to line up. So therefore, whatever the type of your the output of your whole function is, that's also the type of the output of the fold. So then, if that's the case, and we know that fold left outputs a B, then we can essentially copy this type definition somewhere. Let's do it here. And then instead of the B's, we fill in the output type of this list. So that B becomes a list of lists of T, that one as well, that one as well, that one as well, and then that's it. And then if we consider what we need for fold left, well, operator, like the reducing function, tends to be something that you have to define yourself. And the starting value in this case will be the accumulator, is also something that you tend to define yourself, because different ways of reducing a list require different base cases. For example, if you have a sum, you want to start with 0, but if you have a product, you want to start with a 1. But the list is actually, it tends to be given. And in fact, in the previous version, I'm pretty sure that they actually wrote this already, where they say, well, we give you the list to begin with, and then you figure out what to do next. So now we filled in some known parameter for this XS. And again, the types need to line up. So if we look at this parameter, then it's a list of t. So it's a third order list of t. And if we look here to this XS that's defined in the fold left, then this XS should be a list of A. So then if we turn this into a list of t, then essentially what we're doing is we turn that A into a list of t, because now these two are the same. They're both third order lists of t. But of course, because the A is at other places as well, we also need to change those A's to a list of t. And then we end up with a giant type definition, which I'm going to put on separate lines real quick. That works. And keep in mind that we haven't done anything yet for filling in the other parameters, but we do have a better understanding of what the types of those parameters are. So let's first do our starting value. That should be relatively simple. The starting value tends to be something as small as you can get, and when you're working with a list, that is it tends to be the empty list. So let's try that. So let's just put in the empty list. That works because this accumulator is a list as a whole, so nil is a perfectly fine value for the type list of t in this case, or actually list of t in this case. Then we get to the reducing function, which can be quite complex. But when you find a function that's very complex, it tends to be the case that you either need some dirty trick, like I showed you with the nested for comprehension, where you take one element from the list and then you use that one to generate another list, and then you do a Cartesian product of those lists, meaning all possible combinations. So it's either a dirty trick, or you need a function that was written previously. So let's just, and this is just about the types, let's consider looking for a function with this exact type definition. Yeah, maybe this should be at a different line. So if we look a little bit up, we're looking for a function that takes two lists of something, some general type, and it returns another list of that same something. And in fact, if we look at the type definition of concat, it's exactly that. I mean, sure, the t might not be there, instead of it's an A, but again, it's a general type. You could call this whatever you want. It doesn't even need to be a single letter. It could even be like this. And then it actually still works. So it doesn't matter that they're not exactly the same letter. They are still both general types. So then now we found a function that fits this type definition that we've already defined. So let's just try and fill that in. And in fact, this is probably an issue because it doesn't know the type of this nil, which would be a list. Actually, a list of type t, because that is the same type as the output of the whole thing. And now it's still complaining. Probably because we didn't implement these. Maybe also because we didn't do, or I didn't do, this nil like that. No. I thought that this might have been the case because you need some lists to start with, possibly. It's either nil or nil colon nil. This is, yeah. So this is like, when you have nil at the end of the list, that just indicates the end. But if it's over here, then it indicates an element. So then the only element in this list of t is a nil. Do you want to call concat right? You want to call concat right, not concats. Ah, you're right. That is the issue. Yeah. So then now maybe it works with just nil as well. Yeah. And if you think about, now you've lined up the types. That doesn't necessarily mean that it's correct. It's a very good guidance tool, but it's not always the case. So let's think intuitively about this, about also the way that if you fold numbers with a plus, then how would I do that? Yeah, so if you think about concat, then you take two lists of lists and you turn it into a single list of lists where every sublist is concatenated to each other. So, for example, if you have xs equals, I'm going to use shorthand syntax again, 1 1 comma 1 2, and then 2 1 comma 2 2. This is to indicate the dimension of the list, basically. So 2 3. So this is a first list, first element, first list, second element, second list, first element, and so forth. And then you have xs. And that is actually essentially the same thing. I'm not going to discriminate between xs and ys. So then let's turn this into, actually let's make them negative, why not? And then we can say that this is also minus 1 3, minus 2 1, minus 2 2, and then we'll stop here. And then when you call concat on these two, and that is not curried, so that's xs comma ys, that results in yeah, so that will be because you first, you take this one as the base, and then you append this one to it, then you move over to the next sublist and you take this one as the start and you append this one to it, so then the result would be 1 1 1 2 minus 1 1 minus 1 2, and then also minus 1 3. That's the first list that you concatenated, and then you do 2 1 2 2 2 3 minus 2 1 minus 2 2. So then these are the elements of xs, these are the elements of ys, and then this is of xs again, and this is of ys, and that is for just two lists of these. But really, why stop there? Because you might as well just do it for any number, because you could have this resulting list and then you can add maybe a zs, where you say, kind of run out of signs now. Let's start with I don't know. Let's start from the back. 9 1, and then 9 2, 9 3, and then just we have a single 9 4 here. And then you might as well just call concat on this list, and then concat with this one again, and then the resulting thing. Let's see. Let's do it like a calculator. So answer. Like this. And then you just append 9 1, 9 2, 9 3, and then 9 4 to this part. I suppose it should be 8 4. for the sake of consistency. So, you know, you can really do this for any number of lists, because you can always just append the result, and that is exactly what you can use a fold for. So then intuitively, this concat function is something that you recursively apply to some element in your list and the previous result. So if you just put xs, ys, and zs into a list, you can just immediately get this one with concats. Yeah. So I hope that makes it clear why that will be the answer for exercise 3. And I think I'm going to just finish rewriting that association list real quick and run you guys through why I think update with should be in here. It's not in there officially, but if you still have the mental fortitude to listen to me, then you're welcome to stay for a few more minutes. So then let's say, you know, when you have say for example that you have your keys as strings and your values as numbers, and you have a poem, for example, and you want to count how many times each word occurs. So you split it into a list of strings, and then, you know, you recursively put each word into the association list, and you keep track of the value of how many times it's in there. The issue that you then have with it is, you know, say that you recursively do it again, and there's already a word in there, for example, that's probably in there a lot. Then you have to give a value, as in what the new value is. Well, what you could do then is you could maybe say, you know, say that you have val kvs of type association list, where the keys are strings and the values are integers. So you know it's something to find later on, and say that the word the is already in there and it's counted once already. Then if you want to update that value and say that it's 2, you'd have to write something like kvs.update, where you give the key the, and then you give the new value, which we know in this case will be 2, but if you were to do this recursively, then you would need somewhere to update it. So what you could do is KVS standing for key values or key value pairs. So you could do KVS dot value of, and then you just give the, and this would work. But first of all, you run into the issue of getting here. If the value that you're looking for isn't in there, what do you do then? Which is very common, especially in the beginning when your list is empty. And also, you're looping over the list in update once, and you're looping over the list in value of also once, so you're looping over it twice, which is rather inefficient. So you might as well say, well, I'm going to update with, and the types are relatively similar, where you have a key of type k, and you have an let's call it an update function of type from some value to a new value. And then we can essentially just copy this whole thing here. And the issue that we have now, actually, now that I'm thinking about it, is that what if you don't have a value? So I suppose you would have some sort of a starting value, let's call it z, also of type v, that you give if you don't find the correct key. So you need some starting value. And in this case, let's say, well, if you found the correct key and you want to increment it by 1, for example, then you want to do this update function on the value that was previously there, and then that's it. So in this case, you say update function and z. And then now what you can write is something like, assuming that this KVS is still the case, you can call KVS dot update with, and you say, well, I'm going to look for the word the, and if I find it, then whatever that value is, I want to increment it by 1. And then, of course, if you don't find anything, then the first value should be 1, because then you have 1 occurrence of it. Yeah. All right, I think that's it. Yeah, I'll make sure to upload the all these contents to the drive folder, including I think I actually updated or uploaded this exam to it already. It's in clean, however. This is complaining because of that. So that is, yeah, sure, we'll do it like that. Updates with. Yeah, I'll upload the presentation as well. Upload poker hands, and I think that should be enough to prepare you a bit better for the exam. So thanks for joining, and thanks for listening, even though it's 6 minutes over time, and good luck on the exam.